So we have the chassis all set up here for the size in which it will be. And we have the electrical motor that drives the system here. That's ultimately going to raise and or lower, but not so much lower, but mostly raise the toilet seat so that the boys who are unreliable and disgusting will pee into the bowl without messing up the toilet seat, which happens so often. I don't really know why. Why is that? Seriously. How is it so difficult to raise the toilet seat? Come on, right? How difficult is it? I want to know how difficult it is to raise the toilet seat. So if the toilet seat is here and the cover is here, right? Why is it so difficult to lean down just a little bit? Just lean down just a little bit and put the toilet seat up. Just put it up. And then when you're done, put it back down. Put it back down. Is it that difficult? You know, in our house, you're not allowed to wear shoes, right? So you take your shoes off, and in Japanese, we place them in an area called a genkan. Genkan is the place where you put your shoes, and then you also then put on your slippers, your house slippers, where you walk around in your house slippers. So when the girls were young, friends would come over because we live in the United States. Their friends come over. We, fortunately, in our house, we have a genkan, and it was called a mud room. Most Americans would call it, but for us, we use it as a genkan. And there's a shoe shelf where you put your shoes, nice and clean, orderly. You put them in, and you put them into the shelf, right? Put them into the shelf, into the proper level for you. If you're a child, you put them down here because you can't reach all the way to the top, and the tallest person would be me. Yeah, put them on the top shelf. Okay, just take those shoes and then you take those off and then you put on some slippers. Right, so when the girls were young, their friends would come over and they learned how to take their slippers off because at our house, that's what you do. You know, that's what you do. And then of course, right near the door, what you would see, if this is the door, right, and here's the hallway, right, this is the door going outside, you got your little door window here. It is not a jail cell. Keimusho, as we say in Japanese. It is not I don't even know what that is. Anyway, so it's a door window. Anyway, we used to have, before we made the sun porch into or the mud room, as you might call it, into a genkan, we had a shoe shelf over here. So the door would open, and then the girls would and their friends would put the shoes here. But originally, what they would do, before I taught them how to do it nicely and do it well, their shoes would end up all around here, so the door couldn't open, which is like, all right, you're not thinking logically because you're just a child, but come on, all right? You put your shoes in front over here, and the door can't open, so then you just have a mess. So then because I worked from home for most of my career, I would have to put their shoes in the shelves. And it's like, girls, come on. All you gotta do is put them over here. Gotta put them in the shelf. It's not that difficult. They're over here, right? And then eventually they did. And then it was nice and organized and nice and clean. And then they would go back to their homes and they would like destroy their homes because they would like put them all over the place. Well, it's the same with bathrooms, right? Like, open the seat, raise it up if you're a boy, and then you pee, because remember this is the universal pee. Pee into the bowl without the seat down. It goes up. And then when you're done, it goes back down again. So that's what we're trying to build here. We're trying to build a system where that's going to be automated and it's going to be clean. Just factor in that other people live with you, and let's make it nice and clean. Okay. So remember, this is our little, the transducer, the energy harvester, the transducer. That's the transducer. It sends back electrical energy to what will be the hydrogen power engine behind it. So we've got a lot of space to work on that, but the mechanics behind it opening and closing, because this is overdone mechanicals, needs to be exorbitant and fun and ridiculous. So the electrical power that turns this here, and open and close. All right. To accommodate that is going to be our typical overdone mechanicals type of features. Are we keeping ourselves entertained? Yes, we are. Yes, we are. My little one, daughter, just got a puppy. What's today? Today's Saturday? Exactly a week ago, she just got a puppy. And her voice has changed. Now, when she talks to the puppy, as opposed to me or friends, she raises her voice several octaves, and it's kind of like, who's a little boy? Who's a little boy? Who's a little boy? Who's a good little boy? Who's a good little boy? Who's good? If you're a parent of a dog, and by the way, disclosure, I made a mistake in episode number 1, which is the first episode. I referred to Ren as a hamster. Originally, Ren was supposed to be a hamster, but I made it into a dog instead. I don't remember why, but maybe it had to do with the fact that the character, Ren, is supposed to be, helpful and attentive and obeys, follows rules, kind of. As opposed to throwing a wrench into things, uses the wrench to his opportunity to make things better. Hama and Ruli, Hama being a cat and Ruli being a bunny, you have a dog, cat, and a bunny. So apologies for referring to Ren as a hamster, as he originally was going to be. Although Ren could look like a hamster. It has some of the colorations and the shape. So it could be if the body was a little bit different. But Ren is a dog. So sorry, Ren, I apologize. I don't know why. It's just my ADHD kicking in all the time, which makes things a little bit complicated. And we're going to start building the structure on which this sits. So underneath here is the metal. This is the frame on which it sits. Let's make it go like that. Significant enough where it looks like it's holding up something that's heavy. Oh, I see. That's the ground there. So the ground being more or less at this part of the grid. There you go. All right, very cool. So this is what holds the whole thing up, the mechanical parts. That's what holds that whole thing up. And to make it fun, we will obviously add stuff around this to give it some more life. So that is the skeleton that holds the electrical motor up. And in the meantime, we need to be able to, we need battery. So the battery will be contained here. You know what I like a lot about batteries today is that they certainly last a lot longer. They're much more efficient. But you don't have to stick your tongue on the batteries to see if they're still a charge. Now, yes, it sounds ridiculous, and many of us have done it and probably wouldn't admit to it. But checking to see if a battery still has power by sticking your tongue on it is probably not the best idea, especially if it's alkaline or if it's lithium and it might be leaking, especially if it's alkaline, if it's leaking. But also, you're sending electricity through your body, which you probably don't need to be doing. And who knows what's been on that battery. And yet, I've done it many times. We use these lavalier wireless systems that had usually 2 AA's in them. And those AA's, you either use rechargeable ones or you just used a whole bunch up that you'd buy at, a big box store, you'd buy a whole bunch of them. And you'd go through them pretty quickly. That becomes also an environmental issue because, where do you put all these things after they're done? So what we want to do is create a system in which this battery is not going to need to be replaced for maybe 10 years, something like that. And we are finding that batteries last longer now than we even imagined. So something that's supposed to last, let's say, a couple of years ends up lasting for even decades. For example, if I type in, all right, does Voyager have a battery? All right, well, Voyager 1 and 2 spacecraft are powered by nuclear batteries called radioisotope thermoelectric generators. All right, how long was Voyager's battery expected to last? All right, 4 to 5 years for a primary mission to Jupiter and Saturn. However, the nuclear batteries, the radioisotope thermoelectric generators, RTGs, degrade so slowly that NASA engineers have kept the probes operational for nearly 50 years by carefully shedding non-essential systems. Sounds like something that might need to be done for people who are unwanted in society. We're gonna have to shed your non-essentials, your systems. Yeah, scientists are not expecting you're gonna be lasting too long, especially if you get rid of those non-essentials. Anyway, so here's the battery system, and let's see, that's gonna house quite a bit. Now, let me find out how much wattage does, actually we don't really know. We need to figure that out. How much wattage will be needed. We need to take a look at wattage. We need to take a look at voltage. And we need to take a look at amperage as well. So I don't know really much. I'm not an electrician. I would never claim to know much about. In fact, my father-in-law had taught me several times the difference between wattage, voltage, and amperage. And I still sometimes get them confused. And he's patient with me. He was an electrical engineer, so he knows a lot about it, and was also a professor for many years, so he could explain things. I'm just not a good student. I am a bad student. I am sitting facing the wall in my chair because I am wearing a dunce cap. And I'm wearing a dunce cap facing the wall because I'm a bad student. Actually, I was not necessarily a very good student. I ended up for the last 6 years of my schooling, elementary, K through 12, so the last 6 years would make it 6 through 12. No, 7 through 12. 7, 8, 9, 10, 11. Oh, boy. It's just really sad that I can't make simple math work for me. I was a distraction. Can you guess? Can you imagine me? A distraction, yes. Yes, I was. So energetic, we can't control them. Back then, no one really knew about ADHD or ADD, as it used to be called. No one knew about that. I was so energetic, had such a difficult time focusing that they used to give me an extra hour or two to take a test. Although the last 6 years of my K through 12 career, which was 7th through 12th grade, I was in the honor roll. Actually, from 5th grade on, I was in the honor roll. Always did ultimately very, very well, but I needed extra time. And sometimes in the classroom, I would be reprimanded because I would be fidgeting or making noise, or you know those old pens that had many colors? Click, 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 click. Many kids do that. I did it double. Click, 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 click. Oh yes, 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 yes. And you laugh. No, don't laugh, because you've probably done it too. If you're watching this, you probably have done it too. I was non-attentive. I was distracting. I was distracting. Very good. So that is our battery system. Now this battery system is going to need to feed electricity into this engine here. So let's start to build that. This will be our battery. Sideways because it's easier for me to draw this way. Are there any of you out there who are illustrators who find yourself drawing things at an angle? If you are one of the angle drawers, that actually sounds like a bad name for underpants. Angle drawers. That's for people who don't put their pants on straight. Angle drawers. Little Tommy, have you put on your angle drawers? Okay, that's not even straight. If any of my overdone mechanicals was actually made into an actual device, if they would actually win an award for stupidity. All right, that is our battery. And then now we need to send the power from the battery to the engine, the battery. How does a hybrid car battery send energy to motor? Let's look here in this diagram. One of these diagrams. Oh, that's an interesting one. So this is the battery, and it sends the electricity to the motor, and then the motor turns and it feeds the wheel. Oh, sorry, the wheel is recharging the motor. Right. We are going to send the power directly from the battery. Yes, correct. Okay, battery. And then we send it to the motor which turns this and this, ultimately to this. And then as the toilet is closing, going down, it turns this, sends electricity and energy back to the battery. So does it go to the battery or does it go to the, no, this one needs to feed. We're gonna go to this one. This one needs to feed its power to the hydrogen engine. That's just for that spark, to get the hydrogen engine running. So we're gonna make that go all the way here. All the way there. Ooh, that's interesting. AC power, DC, high voltage, DC. Oh, there's so much to learn. I love this stuff. Onboard charger, DC converter, 12-volt battery. All right, DC converter, because, right. And it's the inverter. I can't forget about that. The electric motor, and then we have the thermal management system, basically the little gills there. Okay, that's fun. Now we also need to add a structure skeleton that holds up the battery. So we're gonna give it little legs here. Very good. Sitting on that. That does not look straight, but that's okay. Overdone mechanicals, again, is not about absolute accuracy. It is about exploration of opportunities. It sounds like something a politician would say. We're not going to solve the societal problems or political issues that we're having. We're going to expand our mind and think about alternatives for how to address these systemic issues and in a convoluted way, talk about it. Now, what's really cool is we're going to add some little features to all these little things. So we start to get an overdone mechanicals look. The overdone mechanicals look is convoluted. I love that word, convoluted. I will say it in so many different ways that it won't even make sense anymore, which in and of itself is convoluted. I'm going to putting the con back in convoluted. Otherwise, it would just be voluted. And so the battery is going to have some little extra things on it. And each battery is going to be connected via some kind of maybe a capacitor or a redistribution. I also don't understand how large batteries or systems like in a car or even a laptop. I remember once when one of my daughters was very little, I taught her how to take apart an early iPhone, MacBook Air. And the battery had gotten down to the level where it would only last like 20 minutes. So we bought a battery online at this place called Otherworld Computing, where I buy a lot of our computer equipment. And we opened up the MacBook Air together and then took out the battery. And we noticed that the battery had a number of different cells, maybe, or these different pouches. But then what I wanted to know, how do each of these pouches talk to one another? Does it go from one side to the other and slowly drain it out? Or do they all work together? Or are some of them for certain things? Or, that's not something I never looked at, but we can do that right now. I'm going to type in here, how do prismatic cells in batteries operate in tandem. Prismatic cells operate in tandem by being tightly arranged in bricks or modules and connected via electrical links called bus bars. They operate in two primary functions. They connect positive to negative, adding voltage to meet motor system requirements, or connects positive to positive, multiplying total capacity amp hours. Oh, I see. The bus bars are what connects them, and these are bricks. Bricks. Okay, so these are bricks. So these are the bricks, and these are the, oh, okay, so these are the, I guess these are the bus bars. We can make those the bus bars. That's kind of cool. Now we need compression. So the compression are these little layers that I added here. These are, oh, okay, all right, well that makes sense. I'm gonna add compression to all of them. I'm also gonna add compression in here. And I'm gonna add compression in here. Again, I don't know if this is all that accurate, but I'm just imagining this is something like what would be needed. All right, okay, so, and each battery has some kind of a, I don't know, indentation, because it makes it look fun. It makes it look interesting. And also it needs to have a label, like which brick is it and what's the capacity, just in case you need to remove one and put one in. Oh, so they could be interchangeable. So to be interchangeable, you need to be a quick release. So here's the quick release. That's the quick release. And that way you could pinch it, pull it out. That means that this needs to be all in a larger frame. Okay, so this is the frame in which the battery sits and is housed. And then now we have a removable pouch, removable bar, and you can replace that bar just in case one of the bars goes down, or you don't have to replace the whole thing because batteries can be expensive. Well, we've got the battery, we've got the electrical motor, and we're gonna build the next part. The next part is gonna be the inverter and the switches for which the electrical system would have to turn it forward or backward, meaning turn the wheel one way or the other to close or open the seat. So that's what we're going to do next. We're going to do the inverter, and then we're going to do the switches. All right, well, be overdone and be mechanical.